Welcome! In this video I'll show you how to solve problem 6.16 as it appears on the third edition of Griffiths Introduction to Quantum Mechanics. This problem studies what happens to the Balmer lines now that we have the relativistic and spin orbit corrections to the energy. So the Balmer line is this red line that comes from the transition from n equals 3 to n equals 2. And now that we have these additional corrections, what we will see, and I don't want to spoil too much, but we'll see that the sublevels n equal 2 and n equal 3 actually split into different levels. So the degeneracy is partially broken. And what this means is that now we will have several transition lines, which will be, of course, very packed together, right? The corrections are very small, but still different lines. And that is precisely what we want to study. So let's take a look at it. The question or the problem is the following. It asks us to determine into how many sublevels n equal 2 and n equal 3 split into, and then find their energies. We will then draw an energy level diagram showing all possible transitions. And finally, we will determine the energy of the photon from each transition, and of course, also its frequency. So let's begin. First, we need to understand the sublevels n equal 2 and n equal 3 a bit more. So what is the transition energy, normally? No corrections, no weird quantum mechanics 2 things, just normal, regular quantum mechanics 1. So what is this energy? Or the energy of the photon from the transmission, right? So this energy line is a photon, it's light. And what is the energy of a photon? It's going to be h nu, right? The frequency, h times the frequency. And this is going to be equal to the energy of the first state, or the first level, sorry, times 1 over, and this is the initial state minus this final one, right? But in this case, it starts in the third level, right? So it's going to be 3 squared, right? It's squared, by the way, sorry. And the final one is 2. So this is going to be 2. So what does this mean? This means then that we get E1, this is equal to 1 over 9. Oh, whoops, not equal to, sorry, multiplying. So 1 over 9 minus 1 over 4. So we have to take common denominator here. So just multiply through. And what do we get? So up here we will get a 4 minus 9. And this is all divided by 36. So this would be minus 5 over 36. So we get minus 5 over 36 times E1. And this is, of course, equal to h nu. So what is the frequency then of this transition? Or maybe we can do both, right? We can calculate the energy first. So this is, of course, equal to the energy from this Balmer line, EB. So the energy from the Balmer line, whoops, there's supposed to be an E first, EB. So let's calculate it. So what is E1, by the way? I hope you remember. E1 is minus 13.6 electron volts. So this right here is minus 13.6 electron volts. So we have minus 5 times 13.6 divided by 36. So we get, right, 5 times 30.6, yeah. So we get 1.889 electron volts. I did this to it's 5 times 13.6 divided by 36. Just double checking. Yes, okay. And this has to be, of course, equal to h nu. So what is the frequency then? So the frequency is going to be this amount, 1,889 electron volts, divided by h. Now, you can do one of several things. You can use h, right, the Planck's constant, in units of electron volt, or you can use or transform electron volt to joule and then use the h as, the regular SI units. It doesn't matter. Just use whatever makes you happy. I'm going to transform the electron volts into joules, and that's easier for me. So this is I'm going to have to multiply this by 1.6 times 10 to the minus 19 joules per electron volt. All right. So what this means is 1.889 times 1.6 minus 19. And now I have to divide this by 6.626 exponent minus 34. So this means that the frequency is going to be 4,56 times 10 to the 14th power hertz. And what does it mean in terms of wavelength, right? I mean, if we are already doing this, might as well. So what is the wavelength then? Well, we know that, there we go. So we know that they have a fixed speed, right? So they are traveling, the light travels at speed c, the speed of light, and this is meters per second. So meters is unit of this, and frequency hertz is 1/second, so we have to multiply this by lambda. So by nu. So this means that lambda would then be c/nu. Right? This is just kind of a quick way to remember the formula in case you don't know it by memory. I always like to have, like, I don't know, do a bit of dimensional analysis if I don't quite know the formula. All right, so we have to do this to the minus 1 power, multiply by 3 exponent 8. So this means that this is going to be 6,577 times 10 to the minus 7 meters. But we do like to work with nanometers when dealing with wavelength of light. So let's put this as nanometers. Now, nanometers are of the order 10 to the minus 9 meters. So what we have to do is basically move our comma 2 steps and put the equivalent up here. So basically this will be 657,7 times 10 to the minus 5 nanometers. Oh, sorry, this goes into nanometers, sorry. So there we go, 657,7 nanometers, there we go. Almost messed it up, but there we go. So now we have the frequency, we have the energies, all good. This is the energy and frequency and wavelength from the transition from n equals 3 to n equals 2. All right, that's part number 1. We haven't really done anything new. Now is where the fun will begin. So let's start by looking at how many sublevels n equals 2 and n equals 3 split into. So let me go to the next page, and here I have the formula that we have found in the past. Right? This is the formula for the fine structure. So let's begin with n equal 2. So let's see what happens with n equal 2. If we take a look at this formula, in order to use it, we need to know what value for j we will use. How can we know that? Well, j is L plus S. Since we're dealing with the hydrogen atom, the value for S is fixed. So S is 1/2. There's nothing to change there. So all we can change is L. So, and what are the possible values of L? Well, I hope you remember from what we saw in the previous course of quantum mechanics. L can be, in this case, 0 or 1, right? It can't go quite up to the value of n, and there has to be an integer, or at least integer steps. Okay, so this means, of course, that if L can be 0 or 1, then J can be either 1/2 or 3/2, right? This is when L equals 0, this is when L equals 1. So let's begin with the case J equals 1/2. So J equals 1/2. So now we have to take this formula and plug N and J in. So the first order correction to the second energy level is going to be E2 squared divided by 2mc squared, 3 minus 4 times n is 2, so this is 8, divided by j plus 1/2. And since j is also 1/2, this will be 1. So this right here will be minus 5. Now this right here we will actually encounter quite often. So let me rewrite it. Since E2 is E1 over n, right, and all of this squared, what we have is going to be the following. So this is times 1 over 2mc squared, and this is multiplied by minus 5. Now, what is this? Oh, by the way, n squared here, sorry. So what do we have here? Now, there are a few things to note. So we have 1 over n to the 4th power. Maybe let's call this gamma, and let's solve it separately, because as I mentioned, this will pop up in every single calculation we make. That's why it's useful to calculate it only once. So let's take it separately and calculate it. So this is going to be there's going to be a factor of 1 over n to the 4th power, which will depend, of course, on the particular energy level we are dealing with. That's why I don't want to include it into this constant. We will deal with that as it pops up. Our constants are E1 squared divided by 2mc squared. So what is this? E1, this is going to be 13.6, well, minus, but it's going to be squared, so the minus sign will take care of itself, times 1.6 times 10 to the minus 19, because this is in electron volts, so the 13.6, we want to go to joules, so we can work with this mc squared in terms of SI units, and then I will convert back to EV. You can also convert these into EV units, whatever you want to do, it's fine. It doesn't really matter. So since this is rest energy of the electron, maybe that would have been easier, but I already went this route, so whatever. So this is divided by 2 times 9.1 times 10 to the minus 31 times, this is going to be 9 times 10 to the 16th power. And this is, of course, well, it's not in EV yet. It's actually still in Joule. We haven't done so for now it's still in joules. All right. So let's multiply through. So 13.6 times 1.6 exponent minus 19, and all of that squared divided by 2 divided by 9.1 exponent minus 31 divided by 9 exponent 16. And now we have to go to EV, and for that we have to divide by 1.6 exponent minus 19, right? So divided by 1.6 exponent minus 19. So we end up with this being 1.806, actually 7 if we're going to end here, times 10 to the minus 4 electron volts, of course. All right, so this is the value for gamma. Let's now put it all together. I'm going to keep it here because, as I mentioned, we will be needing this in the future. So let's plug it in. Instead of this beast, this is going to be 1 over n to the 4th power. Since 2 is, n is 2 to the 4th power, it's going to be 16, yes. So 1 over 16 times 1.807 times 10 to the minus 4 EV. So now let's just multiply. So times minus 5 divided by 16. So we get this is equal to minus 5.646 times 10 to the minus 5 EV. To be honest, it doesn't really matter if we go to 3 decimals, but whatever. We already did it, so let's continue doing that. So let's now go to the case where J is 3/2. So the next one. So what do we have here? So if J is equal to 3/2, then our fine structure constant, right, is going to be the first order correction to the second energy levels. Now this will be our constant that we just found, right? 1.80, was it 6? 7. It was 7 times 10 to the minus 4 EV divided by n to the 4th power. And well, and this is of course 16 in this case. And then we have 3 minus 4n, which is 8, 4 times 2, divided by j plus 1/2. 1/2 plus 3/2, because j is 3/2, that's going to be 2. So this is 3 minus 4, which is minus 1. So this would be 1.807 exponent minus 4 divided by 16 and times minus 1. So this would be minus 1.807 1 to 9 times 10 to the minus 5 eV. Great. And as you can see, this is actually going quite fast. So that's nice. Let's now go to the next one. So these are the only two levels for n equals 2. So before we had just one line in n equal 2. Now we have 2, right? That is, of course, because of our corrections. So we have broken some of the degeneracy. Now for n equals 3, what are our values for j? Well, since n equals 3, L could be 0, 1, or 2. So that means that since j is L plus 1/2, it can be, well, for 0, it is 1/2, for 1, it is 3/2, and for 2, it is 5/2. So there are 3 possible values, and thus our level n equals 3 will be divided into 3 sub-levels. So let's start with, with whatever one you want. I'm going to start with j equal 1/2. So in that case, let's now plug it back into our formula. So what we have here, maybe let's refresh the formula just in case we forgot. Maybe I'll write it up here. So our formula for the fine structure constant, or fine structure correction, sorry, is En squared divided by 2mc squared, and then we have 3 minus 4n j plus 1/2. I think that is it, right? I'm gonna double check. Yep, that is it. Okay, but of course we already know what this constant is. That is 1 over n to the 4th power, right? When we simplify, and this is of course now in the 3rd level, first order correction to the 3rd energy level. That's going to be 1 over n to the 4th power, but since n equals 3, that's going to be 9 times 9, which will be 81. And then we have our constant, which is 1.807 times 10 to the minus 4 eV, and then times 3 minus 4 times n. N is 3, so this is 12. And then j is 1/2, so 1/2 plus 1/2, that's 1. So, there we go, easy peasy. So this right here is 9, or rather minus 9. So let's multiply through. So this would be 1.807 exponent minus 4 times 9 divided by 81. And this would be minus 2, quite accurately, minus 2 times 10 to the minus 5 eV. That's number 1. Let's now go for the next one. So for j equal 3/2, then we have that the correction, whoop, my pen lagged. The correction would be 1 over 81 times 1,807 times 10 to the minus 4 eV, right? This part didn't change at all, times 3 minus 12. So far, nothing has changed. The only thing that changes is down here. So instead of 1/2 plus 1/2, which is what we had before, now we have 3/2 plus 1/2. So that is 2. So now it is 3 minus 6, which is minus 3. All right, so let's now multiply. So we get 1.807 exponent minus 4 times minus 3 divided by 81. So here we get minus 6,69 times 10 to the minus 6 eV. However, if you notice, so far all of our results have been in the range of 10 to the minus 6, 10 to the minus 5. So it might be convenient to rewrite it that way, but for now we will just leave it like this, and if we need it, we can do it later. All right, so there is one more correction that we need to do, and that is the correction for j equals 5/2. So in this case, our correction, right, for n equals 3, the first order correction, is going to be 1 over 81 times 1,807 times 10 to the minus 4 eV, 3 minus 12, and now comes the change. Instead of j plus 1/2, we have 5/2 plus 1/2. So that's 6/2, which is 3. So this is going to be 3 minus 4, which is minus 1. So now we get 1.807 exponent minus 4 divided by 81 times minus 1. So that's going to be minus 2.231 times 10 to the minus 6 EV. All right. Phew, so now we got all of our results. Let's get them all together now, because we now want to study the transitions. So this is for j equals 3/2. Maybe let's write it to the side. So this is j equal 3/2 and n equals 3. All right, so where are our other results? So this is another one. All right, so let's put it there. And of course, comment, this is j equal, oh, this is 5/2, by the way, not 3. Whoops. This is 5/2. And this is 3/2. And actually, maybe let's just write it like this, because it's going to be the same symbol all the time. Right? And then we're going to have one more here, which is this one. Right, so we're just putting everything together so that we can look at it a bit easier. 1/2, and then we are going to have something similar. This is going to be 2, 1. Oh my god, that's a very ugly one. Okay, and let's see, where is our result? So this is the case for j equal 1/2. So this is j equals 1/2, and this is j equals 3/2. There we go. So this is j equals 1/2, j equals 3/2. And of course, this is all n equal to. All right, so these are our results. These are the new energy levels. And please notice these are the corrections, okay? So the energy levels themselves are their original value plus what we just found. So we can see that every single value has now decreased. Okay, so let's now draw the diagram, which is another thing that we needed to do. So the diagram would be as follows. We have n, whoops, there we go. We have n equals 2 and n equals 3. And previously we had, right, so this boring line, and the transition was, you know, just direct, right? Nothing too crazy. But now we have 3 lines or 3 sublines coming from n equals 3. Whoop. 1, 2, 3. One, of course, corresponding to, and let's see, which one has the highest energy? So which one basically was decreased the least, right? So the one that was decreased the least was, I'd say this one, right? So 10 to the minus 6, yeah. So it's this one right here. So it's j equal 5/2. J equals 3/2 comes next, and j equals 1/2. And similarly for n equals 2, let me draw the lines again. So the energy levels were also decreased. And which level has the highest energy from these two? So the one that was decreased the least was clearly the one for j equals 3/2, and j equals 1/2 is this one. So the new transition lines are as follows. I'm choosing a color, maybe go for white, I don't know. So we, from j equal 1/2, we can drop down to this, or we can drop down to this. We can also go from 3/2 to this, or from 3/2 to this. And we can also go from 5/2 to this, or from 5/2 to this. All right, so those are our new transition lines. And those are the values that we now want to find. All right, let's see. So I'll now copy this, and we will calculate each transition line in this page. I'll maybe shove this a bit further up. Okay. And put it like in a little box or something. Okay. So let's go for each transition. So let's go from the transition from n equals 3, j equal 3/2 to n equals 2, j equals, actually maybe let's start at 5/2. Sorry, maybe let's do it like that. So let's start at 5/2 and then go to 3/2. It doesn't really matter, but I'm gonna go from 5/2 to the 2 that it can do, then 3/2 to its 2 options, and then to 1/2 and its 2 options. That's gonna be the way I'm gonna do this. So what are each of the energy levels? So let's see, this is literally just the energy difference, just as we did before. And since we already know what the energy levels are, then, you know, that's kind of it. And we want to find the correction, right? So we already know what this base energy is. That's what we found at the beginning, right? Where is it? Right here. So this is the energy of the transition line itself. Now we're only working with these little corrections. So the correction will be just what we find now. So the difference between the two corrections, right? So the difference between the correction to line number 2 and 3 is going to be the correction to the transition line itself in general, including the unperturbed case. I hope that made sense. So let's now start. So what is the energy from n equals 3, j equals 5/2? It's this one right here. So it is minus, no, that's gonna be, you're not gonna be able to see that. So it's minus 2.231 times 10 to the minus 6 EV minus, I said 3/2, so we have to take this one. So minus a negative, so we get plus 1.129 times 10 to the minus 5 EV. And what is that? That is minus 2.231 exponent minus 6 plus 1.129 exponent minus 5. So this is, don't have too much room here. I'm gonna do it here. That's 9.06 times 10 to the minus 6 electron volts. All right, so let's now go from the next case. So instead of going actually, I'm thinking, how can I do this in the best possible way? Maybe I'm just gonna go for a new line here. All right, so now let's go for n equals 3 and j equals 5/2 to n equals 2 and j equals 1/2. All right, so that's the next case. And now we have to do is exactly the same. So what is our energy? Maybe I'm gonna write it like this now. So what is our energy in this case is minus 2.231 exponent minus 6. And we now have to subtract this energy right here. So we get plus 5.646 exponent minus 5. So our result is 5.423 times 10 to the minus 5 EV. All right, next case. So now we are done with j equals 5/2. So let's now go for the next one. So now we will have n equals 3, j equals 3/2, and n equals 2, j equals 3/2. So what do we have in this case? So what is n equal 3, j equal 3/2? It's going to be this value right here. So minus 6.69 exponent minus 6 plus, and it's going to be 1.129 exponent minus 5. So this time we get 4.6 times 10 to the minus 6 electron volts. Easy. Let's continue here. So now we have n equals 3, j equals 3/2, 2, n equals 2, j equals 1/2. So this time, what do we get? We get from minus 6.69 exponent minus 6, we go to this state right here. So we have to do plus 5.646 exponent minus 5. And this would be 4.977 times 10 to the minus 5 eV. Okay, next. I'm gonna just cram everything in here. I'm sorry. Then we have n equals 3, j equals 1/2 to n equals 2, j equals 3/2. So what do we get from this? This would be this energy right here, right? It goes from this to this. So there we have minus 2 exponent minus 5 plus 1.129 exponent minus 5. All right, let me double check that I did this correctly. So minus 2 exponent minus 5 plus 1.129 exponent minus 5. All right, so this time we get a negative. We get minus 8.7 times 10 to the minus 6 eV. And we have one final case, just one last case, which is going to be n equals 3, j equals 1/2, sorry, 1/2, and n equals 2, j equals 1/2. And in this case, we are doing this minus this. So it's going to be minus 2 exponent minus 5 plus 5.646 exponent minus 5. And in this case, we get 3.646 times 10 to the minus 5 eV. All right, now we found every single energy level for each one of these transitions. So what we just found is for each one of these lines, we saw how much energy the photon has that is emitted. So if an electron falls down from one of these, then it's going to emit a photon, and that photon will have the energy that we just determined. I mean, that is the energy that goes additional, of course, to the base energy that the Balmer line has, which is what we found at the very beginning. So the total energy, of course, would be this amount plus the correction, right? So 3.1 in this case, and I don't know where the this was the emission, the Balmer emission, right? So there you would have to add the correction that we just found. And which one depends, of course, on which particular transition happened. All right, so that is it. Of course, now you could go ahead and also find the frequencies. So for example, you just take any of these energies as we did before. So maybe, I don't know, this energy, this is going to be h nu. So of course, nu is simply this value divided by h. And there you get each one of the frequencies. But of course, I think that is kind of trivial. I'll leave you to do that. I hope that the rest of the problem was clear. It wasn't really too crazy. All we did was just use stuff from quantum mechanics 1, and then we just applied this formula. That is the important thing. We just applied the formula that we found, and we saw how it can also be tested experimentally. Of course, as you can see, I mean, the line itself was of the order of electron volts, right? Almost 2 electron volts. But the corrections are of the order of 10 to the minus 5 electron volts. So the correction is very small. So you need like really, really good equipment to actually measure them. That's why it also took a bit longer before we could measure those. So yeah, that is the problem. I really hope this was useful to you. And if you liked it, please make sure to leave a like on the video and subscribe to my channel. It doesn't cost you anything, but it really helps me out a lot. So I'll see you in the next video. Thank you very much for watching.